Right, welcome to the next video, determining the domain and range from a graph and various other things with functions. In the last section, in the last video, pardon me, we started talking about what is domain and what is range. Domain is your input values, your independent variables, your x-axis most of the time. Your dependent variable is your range, your y values, your outputs. Okay, so when we're talking about domain and range, we want to talk about the x-axis and the y-axis. Okay. The domain you can look at here. So we're going to find the domain and range of both of these. The domain here would be everything. So notice how this function is not complete. It actually stops at one point. So this is kind of what we call a piecewise function. It really only has one piece to it, so you could also just call it a limited function. But it stops. It does not go on forever in both directions. It does go on forever in this direction, which means all of our x's eventually will be hit. Negative infinity. But where does it stop? It doesn't go beyond 1. Doesn't go beyond 1. And with an open dot there, the graph is indicating to you that it does not ever actually hit 1. And so we are going to use a parentheses. So little refresher on interval notation now. Let's do the same thing with the range. We're going to look at the up and down in this part, our dependent variable. Now, if we're going to keep going down forever, the range will also be negative infinity. But where is the max range here? Careful, it's not at the closing point. We actually go beyond the closing point. We do end up going to 4 and actually hitting it. And so it will be 4 with a bracket on that side. All right, this one is a far more tricky function. It is a function, passes the vertical line test, but it's got lots of holes. It's got lots of pieces, and as we will talk about later in this chapter, something called a piecewise function, a bunch of pieces put together. But we need to list the domain and the range as a whole concept. The domain here, let's take a look at this axis and see what's going on. Remember, domain and range act as a number line. So let's look at it as if it's a number line. It starts at -5, includes it, and then it goes up, 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 up. It goes back, 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 back to -3 and does not include it. It jumps over -3. And it goes from -3, like really, really close, right? Not actually touching -3, really close, down to -1 and touches it. But wait a minute, it doesn't actually stop there. So I'm not going to end my interval there. That doesn't make any sense. It goes from -1 and then it just jumps down and actually keeps going to 3 where it doesn't include it. So piecewise functions can be tricky because I have to kind of think about collapsing the whole thing down. If I collapse this piece back here, that doesn't actually stop. It keeps going. And so my interval does not stop there. The range, I can do the same thing. I'm just going to look at the number line going this way. Goes from -2, but not including it. It actually does stop. Look at that. We don't have any points in between -1 and 0. So it actually goes up to -1, but again, it does not include it. And then it starts up again at 0 and goes up to 4, but again does not include it. And so I can look at that as if I'm swishing all of those lines and points back to the y-axis. What would I see? I would see this little piece and that little piece. All right. Going along with these graphs, let's work with function notation now. What is f of 0? Remember, that's how that reads. F of 0 on graph 1. And where on graph 2 does f of x equal -1? So let's clean this up a little bit. Sorry about all those. Let's look at f of 0 on graph 1. That means I got to go to x equals 0. So if that's asking if 0 was the input, what is the output? It looks like 4. 4 is the output. So f of 0 is equal to 4. Over here, where is the output? -1. What was the input? Well, here's -1. Careful, there are two. No, I apologize. That was x. Here's -1. Let's see, dot, 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 dot. It looks like the x was here. Uh-oh. I'm so tempted to say 3. But if you recall, -1 is not included in our domain. There is no x. That's an open dot. We're trying to say that it gets really, really close to -1, but doesn't actually hit it. And so we will have to say that x does not exist. There is no x that is going to give us -1 on this function. That's why it's not in our range. Okay. All right, so a little more with function notation. Again, it's all about that input output. Function notation is read f of x. So let's work with those a little more. If you're lucky enough to get f of x equals an equation, you can go very fast with this function notation. So let's do all 4 of these at the same time. f of -1, f of, whoops, f of 0, f of 2, and then this one's unique, f of a. Fascinating. We'll get there when we get there, though. So what does this mean to plug in these numbers? Well, it's just like it was on the graph. We're asking, what if the input was 0? What would my output be? Just this time, we have an input to a function. So we'll go ahead and plug that in. Watch out for that negative there. Whoops. Got to make sure I include that negative. -1 squared is 1, so -1 minus 3 plus 4 ends up being 0. We get a 0 value out of that. That's cool. All right, plugging in 0 now. Squared plus 3, 0 plus 4. This one's really unique, as when you plug in 0, you do start to see that y-axis, which is awesome. 0 is where the y-axis occurred, so you can get your y-intercept this way. Lots of canceling here, just end up with 4. And then 2, got to watch out for PEMDAS on this one. Your order of operations states I must do 2 squared before I make it negative. So I actually get -4 plus 6 plus 4. These two will cancel, and I end up with a 6. Now this last one is a. You're more than welcome to change out the variable. Remember, that's just what you're doing, though. All you're doing is subbing every single x for an a here. And then there's not much more simplification we can do after that. And so that's what we see with our function notation and a variable. All right, let's work with the other way around now. Notice this is f of x equals 4. Our output has been changed to 4. So 4 is what we would get after we plug in an x. If they want us to find the x, we're going to have to do some solving. Subtract 4 to the other side. We only ever want to work with quadratics as long as they're equal to 0. Luckily, by doing that, the 4 goes away on the other side as well. We can take out probably a negative x, makes my life a little easier, although it doesn't really matter whether you take out a positive or negative. We get one side x equals 0, and the other side x equals 3. Those are our two solutions that when we plug it in, we will get 4. Now remember, that doesn't negate the function. That's still a function because 0 gives us 4, and 3 gives us 4. What we would see on the graph is a quadratic. Passes the vertical line test. It's a parabola. What we don't want is 4 being, or what we don't want is plugging in something up here and getting two different answers. All right, let's work a little bit more with domain and range, and we'll close out 9.4. So domain of a function, we're going to list the domain given the equation this time. So given the equation, we're going to list the domain. We're going to list it in interval notation. Rarely use inequality notation when dealing with sets of functions. A lot inequality notation when you're dealing with the higher algebra concepts. But right now, we're just going to use interval notation. It's what we've been working with all year long. We're going to keep going with it. So function here, definitely a function. 2x to the third minus x plus 3. Cubic that has been transformed a little bit, but multiplication, powers, negative or subtraction, and addition all closed. So we are looking at no issues with this domain. So my domain is negative infinity to positive infinity. Looking down here, almost the same function. Almost. We got a lot of similar pieces here, right? This one is x squared minus 2x plus 3. The numerator, totally closed, totally fine, no issues there. But this one's over 2. Ooh, division. Division has a problem. A division, I'm not allowed to divide by 0. Okay, but there's nothing that's going to make a 2 randomly switch to a 0 here. And so this g of x function is also okay. This domain is okay. I don't know if I can make the next statement. I make the statement for the next one, right? I don't know if I can do that same idea. I think this could randomly change to 0. H of x is also a rational function. We have 5 over x plus 3. Now there is a situation in which I could get 5 over 0 here. H of 0 would be fine. Actually, you get 5 over 3. But h of -3, ooh, that's not good. And then explosions, right? Because you can't divide by 0. And so the domain here is going to be, careful, everything below that is still fine. So negative infinity to -3 and -3 to infinity, just not -3. Okay, I'm just saying to the audience, hey, when you're working with this, don't plug in -3, your paper will explode. All right, I of x here, 2 minus x. Ooh, radicals, they also have an issue, but it's only with the even ones. Our even radicals can't spit out negative numbers, remember? So if they're going to spit out negative numbers, we got to say don't do that. So the square root, okay, where does this start though? where would it start spitting out negative numbers? Okay. Well, 0 is actually okay. 2 minus 0 is going to give me 2. I can take the square root of 2. It's not pretty, but I can take it. 2 minus 1, 2 minus 1 would be 2 minus 1 would be 1. Nope, that's still okay. Square root of 1 is good. 2 minus 2 is 0. Oh, it's so close. Oh, it looks like 2 minus anything over 2. Anything over 2 is going to give me a negative. And so my domain can't be over 2. So my domain is everything below 2, negative infinity up to 2. Oh, is 2 okay? Yes, because 2 would give me 0, and so I would include it. All right. Do I have that same issue with a cubed root? No, I do not. Remember, cubed roots, you can get negatives out of cubes. And so when you cube root, you can get negative numbers, right? We can take negative 2 to the third and get a negative 8. So there's no issue when we try to do the opposite. So this one would actually be fine on both ends. This one's all right. This one's all right. This last one, oh, another rational, another rational. No zeros on the bottom, right? No zeros for rationals on the bottom. But I can't really see what's going on in that denominator, right? What on earth is going to make that 0? Maybe if I can't see it, I'm going to solve it. So x squared plus 2x minus 3 cannot equal 0, right? Well, that's, I mean, I could factor that pretty fast. So let's factor that. Let's see, two things that multiply to negative 3 and add to 2. I'm thinking 3 and 1 in some combination, probably a positive 3 and a negative 1, which means x plus 3 cannot equal 0. And x minus 1 cannot equal 0. I really don't know why I put that first one in parentheses. It's not really necessary. So x is not allowed to be negative 3, and x is not allowed to be 1, which means my domain is everything but that. So negative infinity up to negative 3, anything in between them, and 1 to infinity. All right. This last part, notice it depended heavily upon the function itself and whether it was going to have a problem in the algebra. Okay, so when you're determining your domain, think about what happens when you start to do some domains, when you start to plug in some inputs, some independent variables, and then think about if anything could go wrong. If you have any questions on anything discussed in 9.4, please seek out your teacher, and I will see you again in 9.5.